Hi, my name is Marvin Changchiano and I'm from Georgia Institute of Technology. Now I'm presenting about my project which is classifying wake stage in sleep cycle using logistic regression. How many times have our morning alarms woke us up and we still feel exhausted or groggy, even though we believe we had enough sleep? Scientifically, this happened because we were woken up in our deepest sleeping stage, called the non-REM stage. For us to wake up fresh and energized, we need to wake up when we are in our lightest sleeping stage, which is when we start a new sleep cycle, and, and this stage is called wake stage. Currently, there exist some tools that can help people wake up better. On the left is a website called Nectar Sleep Calculator, and on the right is a mobile app called Sleep Cycle. The problems with these tools are first, for the website, it uses static calculations, which means every time people put the same input, it also gives the same output. It is also quite unclear how they actually come up with the time. For the app, it actually uses a smartphone to track a person's movement and sound while sleeping. I'd say these are pretty unreliable tracking, and also it's unclear how, based on the features, they decide to wake the person up. While sometimes they might be accurate, they won't always be. My proposed solution is to create a machine learning based classification model and to use a more reliable feature called electroencephalography, or more commonly known as EEG. This model will be applied to a smart alarm system, which I currently call SmallAlarm. SmallAlarm will accept users' preferred time window to wake up. It will also accept EEG value real-time each second, and from that, evaluate whether the user is in the wake stage or not. If the user is in the wake stage and the time fits the time window, it will ring the alarm. The data is from Sleep Heart Health Study 1 conducted by the National Sleep Resource, which I was given permission to access it. They have 57 and 90 records of EEG data. There's 14 channels per records. There's annotations given by NSRR for each record, which has the sleeping stage for each second. The whole data is around 350 gigabytes and it took 2 days to fully download it. Before I start the process, I want to describe the environment. The whole process ran in my local PC with quad-core i7. It has 16 gigs of RAM and powered by a GTX 980. I also needed a 1 terabyte external hard drive to store the data. Software used are Ruby to download the data, Python for basic scripts and base language, MNE, which is an open source Python library to analyze EEG, PySpark to do a picture extraction since the data is very big, and finally, scikit-learn to train the models. First off, extracting the ground truth, which is pretty simple since the annotation is already in XML format. Basically, each second was labeled 1 if the person is in wake stage, 0 if not. The whole process was quick because XML is pretty lightweight. The part that took the longest time, which is feature extraction. It started with raw EEG data, which is visually shown in that graph, with 8 channels extracted. It results as this n by 8 array, which is then normalized with min-max normalization. After that, the array is manipulated using PySpark to write it in SVM-like format. Applying this whole pipeline to the whole records took 31 hours to finish. After getting the features, I split it into 4,000 training data and 1,788 testing data. The training data was split into 14 folds, 100 records each. Then the model fits in using the folds and evaluated every 500 records. Initially, the model was fitted one by one records. It resulted in a much inconsistent results. With bigger fold, it performs consistently better. Unfortunately, my PC's memory can store bigger folds. I used grid search to find the best parameter for the model. The training time took 75 minutes, and actually, the model was fitted with around 120 million rows of data. These metrics are averaged from testing with 1788 testing data. Accuracy is acceptable, 77%, very nice precision with 94%, and quite a low recall, 17%. However, high precision is more important because it means low false positives, which leads to low chance of mislabeling other stages as wake stage. Small arm can be very useful someday in the future, ideally when it is easier to get EEG data individually when the user is sleeping. The tool can also be improved with more parameter and algorithm tuning. My hope for SmileArm is to have a model that reach accuracy of bleeding edge technology, such as SleepNet or Deep SleepNet, which achieves 86%. Hopefully, it also comes with high recall. Lastly, I will also want to use a much better machine to unlock SmileArm's fullest potential. That wraps up this presentation. Thank you.